Neural network architectures. Here we go. This is a little bit like the feature engineering lectures we had where I went through a bunch of techniques on how to take data and turn it into a format appropriate for your modeling. Well, this is how you do a similar thing in the context of neural networks. And last lecture, we learned about fully connected layers, which is a simple form of a neural network. And in this lecture, we're going to learn about all these other things. Convolutional layers, which takes the notion of filters from computer vision and how to sweep a filter across an input and how would you go about learning those in an interesting way. Max pooling talks about reducing the size of the data in ways that are robust to variations in the input. Activation, we're going to look at a second activation function beyond sigmoid and discuss why you might want to do that. What are some of the pros and cons? Softmax, it's a simple way to turn all the outputs of a neural network into things that are closer to probabilities. Then there are a lot of things in neural network architectures that we're not going to talk about. And I didn't list all of them, but I listed a prominent category of them, recurrent networks. And that is networks that feed back into themselves, which are commonly used for learning things about time series, commonly used when learning things about text. And this bullet here is to encapsulate the fact that there are a whole bunch of techniques in those other fields of neural networks that we're just not going to talk about at all. If you're interested in those, take a different class or go do some reading. I think after this lecture, you'll have enough conceptual framework to start looking at the tools that these other domains use and figure out how to slot them in and where to slot them in. We're going to talk about embeddings and the power of using embeddings. We talked about word2vec in an earlier lecture on feature engineering, and when you're done with this lecture, you'll have a sense on what that is and how you might use it. Residual networks, a very powerful way to learn much more complicated neural networks without getting lost. Then we'll use batch normalization, but I won't talk about too much what it is. I will just point out that it is a thing and give you a quick overview. Then we'll talk about dropout and a little bit on this patience concept at the end if we have some time. I mean, of course we have time because I'm recording it and I can use as much time as I want. But let's get started. So why neural network architectures? Why not just throw neurons out into the universe just like the brain, put all the connections possible? The algorithm Backprop is really good. It should learn zero weights where you don't need anything, and it should learn higher, right? You could get, you guys know, overfitting, underfitting, but you have to set up a network structure that captures the important structure of your domain that you can actually get to converge and that will not drastically overfit the input. And neural networks have so much power that the art of picking the right network structure and limiting yourself to just the network structure you need is a really important part of getting any sort of success at all out of neural network. That's why the architecture is so important. You want to, like I said, avoid the complexity of overfitting and also avoid problems that you cannot converge to the right answer because Backprop just gets confused. So you have to help that search have the right structure. And neural network architectures expressed in little components. We talked about fully connected layers, and you could stack one fully connected layer on another fully connected layer on another fully connected layer. Well, there are many of the structures we talked about on the last slide have the similar property that you can stack a fully connected layer with a convolutional layer, with a fully connected layer, with a residual block, with a softmax, with a et cetera, et cetera, et cetera. And really the art is knowing what those different components do and what's the language that you're trying to express these stacks in to accomplish state-of-the-art computer vision in the case of what we're talking about here. So let's start off with convolutional layers. And remember, in the computer vision feature engineering, we talked about creating a filter. So you can take a 2D image and essentially unroll it, or you can imagine this is one column of an image. And each of these features are a pixel value between 0 and 1. Did I do that? Yeah, they're all between 0 and 1. Now, in the past, we had said, well, you could learn a filter with a fully connected layer that essentially says, well, what are the structures or the combinations of these weights that a particular filter would like to respond to? And that's okay. You can have a filter that's the size of the entire image with a fully connected layer, but what if you want to have filters that are tracking smaller structures or filters that are tracking structures that you don't know where they are in the image? Like with the eye thing, if the eye is very centered, then maybe it's okay to learn a single filter that's the same size as the image, but Maybe you want to learn a smaller filter that you can sweep across the image of the eye and say, aha, there's the corner of the eye. Now I'm oriented. That's what convolutional layers do. They also give you an advantage by reducing the number of parameters that you have to learn. But let's quickly go through a sample of what it would look like. If you had this particular input and you had a single convolutional filter, a layer with one filter in it, and we'll talk about that some more. You say, well, here are the weights of your filter. Now, this is very much like we talked about the Sobel edge detector, except it's a one-dimensional example. We'll see how to extend this to 2 dimensions, but you have the exact same properties. Weight 0, so you get 0.5. Weight 1 times 1, so that would be a -1. Weight 2 times 0.5, so it would be -1 plus 0.5 plus -0.5. And so the activation of this filter when looking at this part of the image turns out to be 0. And then you can sweep the filter along the image and output the activation at each point, just like we did in the computer vision stuff. And you can end up with a complete vector that represents how that filter activated at various points on the input image. Now, there's one little kind of nit that sometimes the width of the filter, this is a 1:2 filter, because it's one-dimensional data and there's 2 elements in the filter. And sometimes that won't line up with your data. Now, one thing that's common to do is to add a pad past the end of your data. Another thing that you could do is to just output a smaller activation than the input, because you could say, well, I can't give you activation 10 because there's no data below x10. So you might just choose to, when you do that convolution, have that be your output. And the output's a little bit smaller than the window by some factor related to the width of the filter and the amount of data that you have as an input. There are some of the basics of what a convolutional layer can do. Now, we're going to go through this a couple more times. So let's talk about the various types of convolutional filters you might have. The previous slide, I said we had a 1:2 because we had one-dimensional input data with a filter that looked at 2 adjacent things at a time. You could also have a 1:3 filter. I mean, I guess you could have, if you wanted, a 1:4 filter, or hey, because we're friends, you can even have a 1:n filter, any size you want. And when you're talking about the fully connected layers from the previous lecture, if there's 10 pieces of data here and you had a 1:10 filter, that's equivalent to what we had before in terms of looking at this whole thing and producing a single output. Now, that's 1D. We're dealing with images, and you could also imagine having a 2-dimensional filter. What that would look like is you bring in your input as actually a 2-dimensional image, just like it is on the disk, and then you sweep this 2:2 plot back and forth across the whole image, and you'd produce an activation output, which is a similar size to this, but which has a higher activation where the filter tends to respond to what's in the image. So 2:2, of course, you could do 3:3, you could do any by any that you want to do. M by N is certainly possible. Part of the art of knowing how to get good computer vision out of a deep neural network is understanding the properties of the filter you're using, understanding the concepts that you're trying to classify, and how large of a window you need to look at to get important subcomponents of that property that you're trying to classify. In this case, if you used a 2:2 window and you put it over the corner of the eye, it's kind of hard to see what's going on there. So you might imagine that something a little bit larger, like a 4:4 or a 5:5, is an appropriate window size with respect to the concept that you're trying to learn or the subcomponents of the concept you're trying to learn. And remember, just as we talked about with fully connected layers, you could clearly see how the outputs of a convolutional layer could be inputs to another convolutional layer. We'll get there. And finally, not really finally, because you can go and go and go and go, but if you wanted to have a convolutional layer that did your color to grayscale conversion for you, you could imagine having a 3-dimensional filter. So it would be the 2:2 by 3 for each channel of the RGB image that you input to the neural network. And so this particular filter can take an RGB image and convert it into a version of grayscale where its conversion is appropriate to the classification task you're trying to do. That is, it's going to learn the weights on how to balance red, green, and blue, and how to combine them into the activation of that filter at the first layer. You could go further, right? You could go to 4-dimensional and you could input an entire sequence of images and create a 4-dimensional filter that converts that into single activation for the output. But let's just kind of focus here for our thought process now and for what you're going to need to do in the assignments that go along with this class. You're going to generally think about creating 2-dimensional filters, sweep them over an image, and then for each filter you have, you get an activation array, which is also 2-dimensional, which has a high value where the filter you had responded to the structure in the input image, and a kind of low or a high negative value where it kind of anti-responds. And of course, we have a single filter, as I showed here, but in general, you would create stacks of filters. So a single convolutional layer might have 1, 2, 3, 10, 15, 20 different filters in it, which you would learn essentially simultaneously, and which would each process the same input, but might respond to a different part of it. So you could learn to identify different structures. And now let me show you a little bit more of what that looks like. This first filter weights _1, which means the weight in the first filter 0, the weight in the first filter 1. Then you have the weight in the second filter 0, the weight in the second filter 1, the weight in the second filter for the second W2 over there. And you could go all the way up to n. There could be 100 of these, there could be 10 of these, whatever amount you want. And then when you run that convolutional layer with, let's say, n filters, the output of it, the input of it is a single image, a single layer, and the output of it is n layers that match that input layer, modulo padding or slight shrinkage because the width of the filter and the width of the image don't quite line up appropriately. And there's a few parameters you can play with there. We'll talk about them when we start to see some of the network architectures that came from papers that were successful in practice. A little bit of intuition about what convolutions are doing. You can imagine that each filter in the convolutional layer is looking for a different property in the input image. And we talked about, like, if you were going to handcraft what filters you would want to use, you might handcraft a filter that looks for an eye corner, a left eye corner, a right eye corner. You might handcraft something that looks for this. You might handcraft something that looks for an eyebrow. And the response of that filter to the input image would be high when there's probably a corner of the eye there and low when there's not. If you apply all of these filters to the input image, you get one output layer, which is essentially high if eye corner. Now, it's not really an eye corner detector. You haven't trained it to be an eye corner detector. This is just conceptually. It will be some sub-feature of the eye that happened to be picked up by that filter when you learned it in the backpropagation process. We'll talk about that. But for the explanation, then you'd have another filter, which is high if whatever the next filter is trying to learn. And you just have a whole stack of images that would have various parts of them lit up. And when you do backprop, like I said, each of these things will start with random weights, each of these filters, and those random weights will tend to head them in the direction of some underlying structure that's in your training data. And maybe you pick to have 5 filters. Maybe they'll find the 5 most important clusters of structure from the underlying data. Maybe you say there's 100 and there's not really that many concepts in your underlying data, so they partially share the learnings so that, like, maybe multiple of the filters make up the information that the eye corner is round, something along those lines. And you won't really control what the filters are learning, what each individual one is trying to represent, but they will each try to represent something that's prominent in the structure. And because of backpropagation, it won't just be prominent in the underlying structure of the data, it will be relevant to the concept you're trying to learn. And it will help reduce the loss to have a filter that understands this component of what's going on in your data, sending information deeper into the neural network. So the response is high where the property is, right? And then you might choose to stack a second convolution after a first convolution. And let's talk about a little intuition of what that might cause. Remember the first one, the I-corner one, and if you look here, there's a series of high values. And what that means is that whatever this filter was responding to, it tends to occur right there. You can look at this filter and be like, where is it higher? Well, it's super low down there. It's at least a little bit high up there. So this filter tended to respond at higher up in the input image than this filter, although they're somewhat overlapping. And then this filter here, wow, it responded the most at the top of the image. Okay, so that's a type of thing that would be in the output of the first layer. And then the second convolutional layer will look across all of the outputs of the first convolutional layer. So this particular filter is a 1 by 3 by n filter, where n in this case is 3. So it's looking at 3 values in one-dimensional data across all 3 or n outputs of the previous convolutional layer. Then this filter in the second layer will be able to respond to the outputs of the filters in the first layer across the window. So they'll be able to say, well, which filters responded on the topmost part of the input image? And I might learn that the presence of the first and the third, I want to add up, and that's positive. That gives me more evidence, and I should have a higher response. But if filter 2 is high there, I might want to have a lower response. And you can imagine mixing and matching the weights. And essentially what this is doing is making a composite of the concepts that the first level of the filters learned, even if you're not quite sure. I mean, you're not learning actually these specific things, but you're learning particular types of interesting things showing up. And so to say that just one more time to belabor this a little bit, just because there are a lot of moving parts, you could say that this filter here outputs a higher value if the combination of the subcomponents is anatomically possible to be an eye. And so that might be the higher level concept that you learn at the second layer. This one might output a high value if it's very sure that there's something funky there. There's a particular type of thing that is often in the data, but is not an eye. So there might be a filter to say like, ooh, yeah, this one is tricky, but I'm going to be a filter to learn and tell you, no, that's not an eye. Don't consider that when you're trying to decide if something's open or closed. And there might be other, maybe not even at this layer, but if you stacked up more convolutional layers, you might learn how these properties blend into even more semantically rich things, like this is a young person's eye, or this is a very old person's eye because of the wrinkles, or, I mean, who knows which layer that type of stuff would be encoded in. Okay, so that's the structure of the convolutional layer. Kind of a little bit hand-wavy, but we're trying to get through a lot of concepts and give you basic conceptual understanding of what's going on. You will learn the weights of a convolutional layer with the backpropagation algorithm. And now I'm just going to walk through the few little differences between what you did with a fully connected network and what you're going to have to do with a convolutional layer. Now, this is a single filter in a convolutional layer. And you're going to have W0, W1, W2. And you want to learn what update should I make to those weights for a particular training sample that you forward propagated through the network. Well, conceptually what you do is, and the challenge of this is that this thing is going to sweep across all these different positions. And so its function in each position might be different, where in this position you'd want to take W1 and make it higher, but maybe in this position you'd want to take W1 and make it way, way lower, something along those lines. And the trick of this is, how do you take a single example and backpropagate it through all of those different contexts to figure out what is the weight update I should do to those shared weights across all those positions when I'm trying to learn a convolutional network. And conceptually, what you do is you just unroll it. You take that same filter and you unroll it into all the positions, even though there's only a single set of weights. And so this unrolling is a virtual unrolling, but conceptually you unroll it so you can remember what happens along each of these edges. So it's an unrolled layer, but each node has to share the same weights. In a fully connected layer, each of these nodes would have its own weights, but in a convolutional layer, looks very, very similar, but they're going to share the same weights. Now, when you do the forward propagation, you get the y hat, then you calculate the error at the output and the error at internal nodes, and all of this stuff is exactly the same from the last lecture. There's no change to what you would do with a fully connected layer. You calculate the error there, and then you backpropagate that error to each of these virtual unrolled copies of that filter. Then to do the weight update, it's exactly the same thing as before, except each of these unrolled copies gets to contribute an independent weight update to the set of shared weights. And maybe this is a long-winded way of saying, like, you do everything you did with a fully connected layer, except you just have a pointer into this weight structure. So when you're doing the update, you're just updating it into the same structure. This guy writes his change, that guy writes his change, that guy writes his change, that guy writes his change. It's another way to talk about it. And to write it out, the delta for weight 1 would be what? Think about it for a second. You would say the error of the first unrolled copy of the filter times the input that it used plus the error of the second unrolled copy of the filter times the input that it used plus the third plus the fourth, and that would be the complete update to that particular weight. I just clicked it one more time and you can see it's the same exact thing with weight 0. Of course, there's the alpha in each step. And then for weight 2, you can see with the pad here, I guess you could do a step associated with the pad. I mean, the pad's going to be there. I don't know. Leave it off, do it. I don't know. Somebody, probably reasonable people, would disagree about what's the right thing to do there. But don't worry, we're not going to implement this convolutional layers in our code base. We're going to use an off-the-shelf neural network learner, so you don't have to exactly know these things to this level of detail. What you really need to know is that convolutional layer, it shares parameters, it sweeps across the input. Each filter creates the response to the image, and then deeper layers of convolution combine the responses of all the filters of the previous layer, and they're shared parameters, and you just do backprop like anything else. That's convolution. Conceptually, what you need to know. We'll show you in a second how it gets used in architectures, neural network architectures that have had good impact. But before we can get to that, there's a couple more concepts that I need to walk you through. One of them is pooling, and another way to look at this is downsampling the input that you have. Now, if you have a 24 by 24 image, you could always just downsample it to 12 by 12 and start from there. Seems to make sense, but if you allow the neural network to do the downsampling and you do it a little bit later in the process than right at the beginning, you can, in some sense, take structure that you learn on a larger image and then throw away irrelevant details, but keep the important structure that is going to help you make the classification you eventually need to make. So it's a nice way of learning how do you downsample the input image in a way that keeps what's important to your classification problem, instead of using just some off-the-shelf sampler that may not be sensitive to what you're trying to do. In this little example, there's the convolution layer. And so let's say we have an eye corner again, like how many times I'm going to say. It's not really an eye corner detector, but for whatever this concept happens to be. And that's the activation that it learns. It's a 1 by 10, just like the input was. But let's say that you know that once you've identified the important substructures of the image, you don't need as much resolution. And when I say you know you don't need it, you just have to, it's just like anything with machine learning. You do some math in your brain about, well, how big is what I'm looking for compared to the size of the filters I'm using, compared to the size of the image, compared to the amount of time I have to compute. And then you do some hyperparameter sweeps once you've kind of oriented yourself in a reasonable space. And based on all of that, you probably determine, hey, I'm spending way too much time processing. So let's do an initial convolution layer to bring things in and to turn them into an activation sort of space. And then within the activation space, let's start doing some downsampling. If you had a max pooling layer, what it does is it'll take a filter itself. In this case, it's one-dimensional data. So we'll have a 1 by 2 max pooling filter. And then the stride, this is a concept I didn't introduce in convolutions, but it applies just as well to convolutions. The stride is you want to apply the filter to the first index in the input, and then you take a step of size stride to determine where to apply it next. So there, and there. And so between the filter size and the stride you choose, it controls what type of downsampling you're going to be able to do. But in this case, a max pooling layer would look at these first two activations, and it would say, well, the largest of those two activations, which means the most that I think there's an eye corner among those two pixel locations or input locations, is 0.12. So that's what I'm going to output from the max pooling layer. Then you take a step down and you'd see you have, a 0.8 and a 0.3. Well, 0.8 is the largest number there. That's the maximum we think that there's an eye corner within that window of data, etc., 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 etc. You can see that this is robust to this data being shifted a pixel in either way or a few pixels in either way based on the stride and the size of the filter. You're able to say across this whole region, what's the most I see the thing that I'm looking for, and summarize that with a single number. And that's often a very, very valuable thing to do. So why would you use max pooling? It's faster because there are fewer parameters to learn, but the way it reduces the parameters is sensitive to what your filters are picking up versus just throwing away the information at the input layer, which might make it harder for this filter to pick things up. It just says, well, your filters picked up certain stuff in the top 20% of the image and the bottom 20% of the image, etc., etc., etc. And that makes overall this more robust to small changes of input and a better way to reduce data than by doing computer vision, hand-tuned feature engineering upstream. And that's a theme in neural network architectures, which is take all the things you used to do by hand, through experimentation, through like, what's the best way to throw away this input? What type of smoothing and subsampling should we do? Let the neural network learn it for you. You don't have to do it. All you need to do is set up the network structure in a reasonable way, layering things using your understanding of the problem, and then the neural network will go figure out how to do the transformations most appropriate to the thing you're trying to predict. And now I'll just give a quick sketch of Backprop through a max pooling layer. Most everything we're going to be talking about is we're going to do Backprop, and all you have to figure out is, well, what parameters go with which weights, and how do you take the derivative of the output with respect to the change of the relevant parameters through that particular layer. So in this case, you start off with forward propagation, and this particular network structure has the input with a single filter, like a convolutional layer here, followed by a max pooling to get to go from this 1x2 output to a 1x1 output or a single output. And you would forward prop through the unrolled filter, and there I believe I've drawn the raw activation and the activation after the sigmoid. Then you would pass the maximum of those out based on the filter and the stride, and there's no additional activation from a max pooling filter. You just pass the largest number through. And from that, you're able to calculate the delta y, whatever, 0.82 related to the input. Then to do backpropagation, calculate the error at the output node. And then this is the same function we had before for calculating the error at an internal node, and it's the same among all the variables that are relevant there. So you would calculate the error at the max pooling layer, delta at pooling layer. And then you'd say, well, okay, how do we push this further back? Well, it turns out that there's zero error along this channel because this channel didn't affect the output or didn't affect anything downstream. All the error goes through the copy of the filter that produced the output that you propagated further into the network. And that means that you percolate zero error through this, and essentially you multiply it by a 1. You multiply the error that was produced here by a 1 to figure out how to propagate that back through the branch of the max pooling that was active and propagated further into the network. And then once you have the error there being 0, the error there being what it is, you further propagate through the rest of the network, and you do the weight update just like before. No, there's no weights to update here. There's nothing to change, but it just affects how the weight updates propagate further back into the network, in that, nothing over here would be updated because of this 0. Okay, well, we got a few concepts: convolution, pooling, softmax. We need softmax, and then I think we're ready to talk about a real architecture. And the point of softmax is that you can have an output layer with multiple things that it's trying to predict. These different concepts, they each will have their own associated Y, and you'll try to learn a set of weights in the neural network that does a good job at all of these simultaneously. And what that means is they all essentially share the same weights, but that doesn't mean that there's any relationship among them. Whereas you might know that the I is only going to be in one of these 3 states. You might like to convert the outputs, the raw Y outputs, into something a little bit more like a probability across these, so that the probability of these things sum to 1. Well, that's what a softmax layer does, in short, is it converts these uncalibrated things into something that's easier to interpret as a probability. And there's the math of it. You say that E raised to the input. So if you're trying to figure out the probability of the I being open, you would take the associated input and you would say the softmax value for that is E raised to this value divided by the sum of E raised to all these values. That doesn't seem particularly surprising to me. Maybe it shouldn't seem particularly surprising to anyone, but this is a convenient way to write it in a neural network because you can take the derivative, and we'll show you how to do that in a second. So you might take these arbitrary activations, and this, what do we know from that? How does it get a 1.2 as an activation? Well, it must not be using a sigmoid. I don't know. We'll talk about why that might be in a few slides, but whatever the case, whatever these values are at the output, then you pass them through the softmax function, and you're going to get something that sums up to 1. Very nice property. Interpret it as a probability with the caveats of all these things, that it's not actually a calibrated probability. It's just something that you can interpret as a probability. And I think if I get myself out of the way, very small at the bottom here, because you'll never need to calculate this. This is how you propagate the derivative through a softmax layer. The change in the softmax for a change in the input is this if we're talking about that particular input, and this if we're talking about the other inputs in this example we gave before. So what this shows is that when we're trying to backprop from this guy, we backprop through there using this as the derivative, and then we backprop through there and through there using this other thing as the derivative, because the outputs of these actually do affect the value of y hat for the probability that the I is open. Okay, that's all I'm really going to go through on the softmax. What you need to remember is that it's commonly used at the end of a neural network when you want to take multiple possible outputs and convert them into something that's a little bit more cohesive and consistent and you can interpret as a probability. All right, our first real neural network architecture, LeNet 5. The task is to look at handwritten digits and answer by predicting the digit that's in the image. Here's the network architecture. We're going to walk through it step by step and try to understand a little bit of why it was set up the way that it was set up. This is from a 1998 paper, so it's pretty old, and computers weren't fast then. Computers have made a lot of progress, particularly with GPUs and all of that jazz. So knowing that there's 60,000 parameters in this network, it's small by modern standards, but it's large in some sense. And this paper still uses sigmoid activations throughout. A couple slides we'll see what another option is and why that's important, but for now, sigmoid. So here's the architecture that we're talking about. There's an input, which is an image, which is 32 pixels by 32 pixels. Here, there's an A, but ignore that A because we're trying to get digits, so there's no A. Well, you could do the same task to try to do optical character recognition if you wanted to. Here's the input. Then the first layer is a convolution layer. And the convolution layer has these properties. It's a 5x5 filter with a stride of 1 and no padding. Now, let me tell you the implications of the 5x5 and no padding kind of in the way people talk about it is if your input image is like this, except this line was too crooked. So let me try that line again. So you have this input image like this. Now you have a 5x5 filter. That means like 1, 2, 3, 4, 5. So the filter needs to be like that. 1, 2, 3, 4, 5. The filter needs to be like that, a 5x5 region. And that filter will output a value for the center point in that 5x5 area. Now, if you had a pad, you could have negative things over here, and then you could essentially slide the filter that way, and you could have outputs at that point and that point. But without the pad, you don't have any, you can't slide the filter outside of the original image. And that means that the space of activations is going to cut off, in this case, 2 pixels completely around the entire image, because the 5x5 filter has 2 pixels activation, 2 pixels, the same on the top, the same on the bottom. And this is a kind of long-winded way of saying that the input is 32 by 32. When you run a convolution layer with this property, with these parameters, you end up with a 28 by 28 activation image. Go from 32 by 32, you cut off 2 pixels all around the tops and the bottoms, and you have this smaller activation window. In this case, there's six filters, 1, 2, 3, 4, 5, 6 filters. Single image layer, gets shrunk down a tiny bit. You're looking for properties that are about 5x5. So you're looking for lines and edges and twists and curves that are about that percentage of the overall image. And you're creating 6 of these property detectors. That's step 1 of the neural network architecture that we're talking about here. Step 2 is subsampling. And to do subsampling, they did what's called average pooling, which is just like max pooling, except guess what? Averaging, right? And the derivatives, you could imagine how you do that. You send a quarter of the, anyway, we'll not get into too much more detail, but the filters are 2x2 average pooling filters with a stride of 2. It's important to think about the size of the activations that you're passing through your neural network layers. That becomes one of the tricky bits in programming, to keep that all straight and to make it so that you're preserving size where you want to preserve size, and you're reducing size where size is irrelevant. You're going to end up probably, if you were doing the iBlink thing, when you do the iBlink thing, you're going to be needing to think, well, what size filter, how much stride, what's the next layer going to have to work with, how do I keep it at nice sized images so that I can continue processing it the way that I want to process it. This average pooling layer results in each of the input activation arrays has an equivalent output activation array where the size is just reduced by the implications of this filter. And in this case, that cuts it in half. So you have 6 14 by 14 activation arrays where there you go. Now the next step is to do some more convolution. And again, they use the same filter size, the same stride, and the same lack of padding. So that goes from 6 14 by 14, except this time they use 16 filters. And remember, because of the implications of the filter size and the stride and the no padding, you cut off that 2x2 strip all the way around, and you go from 14 by 14 to 10 by 10. Then again, with the average pooling, to go from 10 by 10 down to 5 by 5. Now remember, each of these filters works across all 6 of these filters outputs. So these are 10 by 10 by 6 filters, and that's the size of the weight array represented by each of these activation layers that you're going to have to come back and learn. Then, after that second subsampling, you're down to 16 by 5 by 5, and now they have this thing, this full connection layer. And there's a operator which you need to conceptually apply or really apply in practice depending on your implementation. With the tool we're going to use, you need to explicitly tell it, convert from two-dimensional to one-dimensional. What this operator does is it takes all of these filters and stacks them up into a one-dimensional array, and that will be the input to the next layer, which is going to be, let's get a click here, a fully connected layer, followed by a fully connected layer, followed by a fully connected layer, with one output in this final layer per digit of input. So there's the Y for digit 9, there'll be the Y hat for digit 8, the Y hat for digit 0 coming out of the output. You can imagine there might be a softmax there so that you can get a probability out of those. And you have a 400 layer input here to 120 node fully connected layer, which then sends to an 84 node fully connected layer, which then sends to the output layer. What does this do? Let's talk through this a little bit. You take a raw image as input. You find 6 important sub-properties of an image that are about size 5 by 5, and you say, well, where are those important sub-properties in the input? Then you scale it down because you don't quite need all the resolution, and you need to get rid of parameters. You don't want to percolate those parameters all the way down. You want to squeeze it. Then you say, well, I now have 16 important properties, but those 16 important properties are no longer related to this conceptual space. They're related to this conceptual space. So these are combinations of those original 6 important properties in the image. So there's 16 properties which combine over 6 properties which come out of the original image. Then again, subsampling, because you just want to know, were those present? Were they not present? You don't want to know exactly where they were. And then there's a bunch of fully connected layers. So in some sense, you convert 32 by 32 image into 400 activations, which talk about these intermediate properties that the network's going to learn for you, and then you just drop it into a fully connected network of the type that we used before. You could conceptually learn to like this layer and then drop it into a decision tree, 400 features into a decision tree, and then you've essentially gotten all the power of the computer vision and the convolution from the neural network, but this part of the structure is trying to take that and turn it into a prediction. Right. Conceptually, you may not want to do that, but all right, there you go. Now, let me just show you this visualization up here, and it was animated before, but that was crashing something, so I stopped the animation. And with this as the input, these are the outputs of the filters at the first layer. And so they convert. Like this one looks like it's looking for an edge, but on the right-hand side of things. This one looks like it's looking for an edge on the top, maybe in the bottom of things. This one looks like it's looking for an edge on the left side of things. Okay, fine. Now, I believe that what they've drawn here is this layer. These are the 16 filters that take combinations of these filters and output a response. And so maybe you can squint in and you can look and see, do these make semantic sense that those would be more or less relevant to the task that you're talking about, that make useful combinations of this first layer? I don't know. I'm not going to try to justify it. But then this right here is the, I believe, the 2D to 1D with the 400 activations. So that's a way to think about a neural network. This was an important early neural network. It was a long way away from computer or for human level capabilities in a neural network, but it really did take us all on a good step. And when you do your implementation in Module 3, I think we're going to essentially copy this structure and try to tune the elements of the structure for the iBlink task. Moving on, we're going to talk about another type of activation that you can do. Now remember, the sigmoid was very important to add the non-linearity into the network, so you end up learning anything other than just a linear structure. Without an activation, all these layers and layers of neural network just result to the same modeling capability as logistic regression, just a plane in whatever the dimensional space is. So you need some form of nonlinearity, but what you don't need is a sigmoid. And over time, people have found that sigmoids have certain disadvantages and have come up with a much simpler structure, a ReLU activation. And here's the graph of output to activation for sigmoid and output to activation for ReLU. And if I click, I think it'll pop it right up. On the forward pass, the sigmoid is this complicated thing. And on the forward pass, the ReLU is x if x is greater than 0, where x is the input. Otherwise, it's 0. So that's exactly what it says. If this is input equals 0, you output exactly the input over there, and you output 0 no matter how negative the input gets. That's a nonlinearity right here is a critical point where it's no longer a linear function, and that allows your neural network to learn much richer functions than you could do without an activation. It looks simpler, so maybe there's a little bit of reduction in the power compared to the sigmoid, but in practice, the parameter space that you use is so powerful, can represent so many things that you really don't need to get too confusing in this space. And the advantages of the ReLU over the sigmoid outweigh it. And in a second, I'll talk about what those might be. But just to say, the derivative, remember we had this sort of complicated thing when we were doing backpropagation, and that showed up in all the delta H's, this particular structure like that. Well, the ReLU is a lot simpler. The derivative of x is 1 if x is greater than 0. That's pretty simple to take the derivative of. Otherwise, it's 0 because, that's pretty simple to take the derivative of. And that's one of the big advantages is it's just so blindingly simple to do the computations that you need to do with a ReLU versus the computations that you need to do with a sigmoid. But there's even more reasons that it has an advantage. And just to quickly show, that's what I was talking about. This turns into this, and if you were using ReLU instead of sigmoid, you would substitute this into your backprop, and you would put this in right there instead of that. Everything else remains the same. Now, what are some of the advantages of this? It's computationally faster, very easy to do compared to this e to the x stuff. But maybe more importantly, the gradients aren't squeezed. Now, what did squeezed gradients mean? If you remember, it's like the vanishing gradient problem. And the problem is that this thing right here, when you take the derivative, as the sigmoid of x gets very near to 1 or very far negative, the value of the output of this gets smaller and smaller and smaller. And if you remember from the backprop example, every layer that you went back, the derivative, because of this component here, ends up getting smaller and smaller and smaller and smaller. And so you have a hard time propagating errors back through the neural network so that you can do backprop at the earlier layers of the network. And that's a problem, but this doesn't have that property. I mean, it clips the gradients when they have a certain behavior, but other than that, it just lets them go through, and it can pass them through, and they can get much further in general before they start getting squeezed and you start having the vanishing gradient problem. It's very helpful to allow large networks to converge at all. And it has this other property of activation sparsity, which means there'll be internal nodes where you are kind of clipping its output, clipping its activation to 0. What that means is that in any particular forward pass or any particular classification, parts of the network will turn themselves off. And what that means is that you'll be using less of the parameters of the whole network to make any particular decision. But it also means you won't be spreading a single decision that you need to make, or a particular type of classification for a particular X instance. How do I get to the Y? You can instead use part of the network for particular parts of the instance space, and then have through this ReLU nonlinearity, turn off parts of the network for that particular problem and reserve those parts of the network for other problems. And so sometimes it's nice to have this sparsity behavior within the parameters and how you're passing information through the network, so that you don't try to learn every concept everywhere. And there's a little bit more of a, encapsulation of how information is represented within the network. Some non-advantages, you could say disadvantages. You could imagine dead neurons. If there's any neuron that has no way to get X positive is going to always output a 0 and die, and everything related to that neuron can die. That can be a problem. And like I mentioned before, it's less nonlinear. And if you were going to be building a very small network, like we did with simple, fully connected network layers, and you were thinking of using ReLU instead of sigmoid, you may lose the advantages here to the point where this actually starts to become a disadvantage overall. Now, I haven't gone and run those experiments and tried it out. That's just my intuition. You're welcome to do it, or you're just welcome to say like ReLU is most relevant when you're dealing with large, deep neural networks and trying to get them to be efficient and to converge. Another technique that is very important to help large neural networks converge is called dropout. Another important property to learning large, deep neural networks is this notion of dropout. And dropout turns off random neurons at training time. You do this to reduce overfitting, and it's similar to feature restriction in random forests, where if you'll remember, certain of the trees in a random forest are told to, hey, learn this concept a different way. These 14 variables, don't use them, learn it a different way. And so every time you do a dropout in learning a neural network, you're saying, hey, for this backpropagation, learn the concept a different way. Just don't learn it maybe that same way you learned it before. Learn it a different way. And this keeps you from directly encoding so much information about a particular sample into a particular sort of like path through the neural network, because you're always trying to learn the same thing a slightly different way. Technically, what this means is that your error for the dropped neurons is 0, and you essentially just turn them off. But it's very important that at test time, at evaluation time, at performance time, you turn on all the neurons. Dropout is just a function of training time to help reduce overfitting. And so a little example of that, for training iteration 1, whether that's the first sample, the first batch, the first round, the first epoch of complete gradient descent, you might turn off these 2 neurons. And so you would not backprop any error through there. You would not update any of those weights. The second round, maybe those neurons are on and those neurons are off, and et cetera, et cetera, et cetera. In general, in the tools that we're going to use, a dropout is its own specific layer, which every parameter it takes in, it passes it kind of straight out, and some of them it just zeroes out at training time. So it's not a concept that you need to implement in all your different layer implementations. It's something you treat as a special layer. And then you tell this layer, hey, right now it's training time. Hey, right now it's evaluation time. So it knows how to behave. And the dropout layer takes a parameter, which is which % of the weights that pass through it do you want me to drop out? All right, now we got a pretty good toolkit of techniques. We're going to talk about a more advanced neural network from 2012. It's called AlexNet. And the task that this network was built for was more general image classification. Here was a competition that it entered, and it did a really good job at. It got 17% accuracy if you let it predict 5 choices. So you might be able to see here, this says might, and then here are all the different class labels that it predicted. It predicted might at the highest output value, black widow, cockroach, tick, starfish. Here's a boat, container ship. It predicted container ship, lifeboat, amphibian, fireboat, drilling platform. Now this particular benchmark data set, the competition data set, had something on order of, I forget, like 1,000 potential labels. So it's quite a difficult task. Oh yeah, I think it's written right here, 1,000 potential labels. That's the number of outputs from the neural network. And 17% accuracy if you take the top 5 outputs and say, well, is the true class in the image one of the top 5 largest outputs from the network? And that's where we got to. This has 60 million parameters, which is quite a large step forward from the 60,000 parameters in the previous network. And I'm going to walk through how they use those parameters. It's in many ways similar, but just everything is getting bigger and bigger and bigger as we've progressed through the years. The input layer for this task is a much larger image. It is 224 pixels by 224 pixels by 3. That means that all of the R, G, and B channels are input to the neural network, and AlexNet does all the work of taking that and converting it into whatever normalized, whatever grayscale, whatever kind of internal representation it needs. And we'll, the layers that we're going to talk about do that. The first layer that they use is 96 filters. So That's 96 deep there. Each filter is 11 by 11 by 3. So it looks at, about that percentage of the input image and all 3 RGB layers with a stride of 4. So it starts at the upper left-hand corner, outputs an activation, then it moves over 4 pixels before it outputs the next activation. Then it moves over 4 pixels before it outputs the next activation. So this is a similar technique to doing pooling, except you're doing it through the filter and the filter stride. And you're saying, I'm looking for features that are about 11 by 11 in the input image, about, 5% of the width and 5% of the height. And I'm not going to look for them at every pixel. I'm going to just stride across the image and leave a little bit of a gap, because maybe the things that I'm looking for it's not so important. And these filters are going to overlap anyway. It's just that the structure of the things I'm looking for are not 4 pixels or smaller. Everything I'm going to try to identify is larger than that. So let's just not go crazy and try to get activations at every single pixel. And the result of that is you've downsampled the input image to 55 by 55 by 1. I mean, you go from the RGB to each one has a single layer of the output, but since there are 96 filters, you've gone from 224 by 224 by 3 to 55 by 55 by 96. It's the number of kind of like activation pixels you have in your array after doing that. The next step is a max pooling layer. And so it was a 3 by 3 filter with a stride of 2. These are hyperparameters. The joke that they say is that, how do you learn a model? You do gradient descent. How do you learn a neural network's architecture? You do grad student descent. That means you take a grad student, you say, it's your PhD to go and build an architecture that solves this problem. And if you can't do it, you don't get your PhD. And that's how grad students descend. So I don't know. I mean, they try a lot of things, and they struggle with the runtime, with the thought process. They look at the output. Maybe they visualize the internal layers. They're like, oh, you know what? Stride of 2 is the right thing to do here, because it cuts the image down more, and it doesn't tend to throw away the types of structures that I need at this level of my network to do the prediction I'm trying to do. And this is another way to say that people say feature engineering, okay, it's hard. You have to understand stuff. You have to blah, 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 blah. Architecture engineering is even harder than feature engineering. And you might hear people say like, hey, with neural networks, you don't have to do feature engineering. That's one of the big advantages of it. Yeah, sure. If you're able to take an off-the-shelf network like AlexNet and tweak like the size of the input and maybe tweak a little here or here, sure, you're in great shape. But if you're going into a new domain where you don't have the benefit of all of this grad student descent behind you, you're in trouble, man. Like, you and I are not going to go and invent the next neural network. Maybe one of you will. I'm probably not. And it's an exciting time to be in neural networks precisely because there are so many big breakthroughs. I think computational power has caught up to the point where a really excellent thinker in a particular domain with a lot of the right experience is able to create surprisingly new architectural structures, architectural combinations, and make great progress. And that's why you're seeing people reading papers that are coming out almost in real time and percolating the results from those papers into real products. So anyway, it's just a little aside to be like, yeah, I understand there's not a real theoretical justified reason why you would use a stride of 2 there. But there is kind of this meta reason of all these tools coming together in a really interesting way. Anyway, after that max pooling layer, they did another convolution layer. And this time they used many more filters, 256, but smaller filters that go across all the activations of the previous layer with one stride. So some of these earlier ones had strides on them to take information and kind of wring it out of the system. And now they're getting to the point where they feel that the size of the images that they're working with, which is this 27 by 27 or something in that ballpark. I didn't quite calculate what it would be in that frame. Like, that's small enough. That's tight enough. There's no more information to wring out of it exactly while I'm creating these filters, although the very next thing they do is another max pooling layer with the exact same parameters as before. And then this goes on multiple times with 384 filters that are actually pretty small in this new space, but we're only talking 13 by 13. So the input image 224, we're currently at 13. So each pixel represents a large portion of the input image, and you're looking for 384 different types of responses across a pretty large section of that input image, but with multiple transformations to kind of change the representation into primitives that are relevant to the classification problem you're trying to do. Okay, right? Just like walking through where we're at. More and more layers of convolution, convolution layer on convolution layer on convolution layer. And then just like the previous network, there's a couple of dense or fully connected layers, and then a single output layer with 1,000 parameters. And I'm pretty sure there's going to be a softmax over there to tie everything together. And this is an idealization of this architecture. In the paper, it's a fair bit more complicated because the actual architecture had to split across GPUs to get it to converge in a reasonable time. So part of these are learned, I don't even remember how it was. I think this 256 part was split across 2 different GPUs, and then the outputs of these layers were, read the paper. And a little bit more complexity. To reduce overfitting, they did this thing called data augmentation. We've talked about this a few times in our discussions, but the idea is that you only have a certain number of input images, but you can do minor modifications to the input image that allow you to have other data that's totally plausible, particularly when you have these sort of unconstrained images of things in nature. Like rotating it 1 degree is perfectly plausible. Somebody might have held the camera slightly differently. They also do this trick about modifying the principal components, which we haven't talked about yet what that means. We'll have another lecture, and then that'll make a little bit more sense at that point. And they used dropout with a 50% dropout rate. Among the first 2 layers here, they inserted dropouts, I guess, probably there and there after those things. So 50% of the neurons in each of these dense layers were off and not affecting the network, randomly selected for probably each batch of whatever n images that they were able to fit on the graphics cards with the models in order to do the training. Now we're going to talk about one more network structure. You say, why just one? We have inception, we have LSTM, we have inductors, we have transducers, we have blah, blah, blah. Maybe I'm even making up words here. I'm not sure, because I don't want this lecture to go on forever. And then you got to have more stuff to learn if you take another class. I don't want to teach you everything. I'm not that kind of guy. I'm not going to take that away from other teachers in the world. And quite frankly, I think that this is enough concept for this lecture. I mean, there's really a lot to absorb. And the point of this, again, is just to introduce you to the conceptual things that go in to making deep learning as powerful as it is, so that you'll be able to be involved in conversations, and so that if you look at a few papers, you're not totally confused and you have some sense of where they're going, and also so that you can tune your own simple versions of some of these networks to perform well on tasks that you care about, like your homework. Next, we're going to talk about residual networks. Residual networks allowed the training of much, much deeper networks than before. I don't know if you saw the other ones. They were like 6 layers or 7 layers or 12 layers or something along those number of layers. Well, what if you wanted to go to the number of layers that are in the brain, like 100 layers, 200 layers, something along those lines? A simple experiment you could do is with whatever structure. I mean, I don't know, go read the paper if you want the exact answer, but the 20-layer network compared to the 56-layer network, once you had the 20-layer network kind of tuned in, I guess, 20-layer network had lower error on the training set, not even on the validation data. And so it's not that the 56-layer network was overfitting, it's that the 56-layer network wasn't even able to fit the training data. And that is a little crazy, because with 56 layers, there's going to be a lot more parameters than with 20 layers. But it's all of these problems I've been talking about the vanishing gradient, or as you move the backpropagate through the network, the stuff near the input doesn't have as much signal on what to do. You might start to learn things near the output of the network, but the early iterations of training the neural network, there's a whole bunch of randomization at the beginning of it. Then you're starting to learn things at the back of the network. And I guess if that slowly starts to percolate back, you kind of start to zero in and understand the concept well enough at the beginning of the network so the early filters can start to learn something helpful. So you can start to push that in your forward propagation and learn better parameter values at the end of the network. But that's a whole long process. And if the network gets deep enough and you're using sigmoid or whatever else and the activations disappear and you can't percolate backprop from the back of the network to the front enough to start learning at the front of the network, you're going to get stuck. At least that's the theory. And ResNet is a pretty good example that that's probably true because the structure they came up with to address this problem, right, the gradients get stuck deep in this neural network. And here's the very simple thing that they came up with. Remember we were talking about boosting and you said, well, you've learned the function, there's still some errors, now you can learn the residual. And that's what this is trying to do, is that these layers of the neural network aren't really trying to learn the function directly, they're just trying to learn the residual of what a simpler network was able to get to. And this says that you take the input of the neural network and you make that the output, but then you also add in the output of these intermediate layers. How the heck does that work? Let's talk about it a little bit more. If you had a 34-layer residual network to do an image classification task. Now let's walk through what all these different layers say, at least to some degree. 224 by 224 image, same as the other one. Convolution to get you started. 64 filters, 7 by 7 by 3. Remember the other was 11 by 11 by 3, I think, with a stride of 2. Okay, you come up with different parameters. Goodness knows why, grad student descent, I don't know. Then at this point you have a 56 by 56 image because you've done like a little bit of pooling and this to take the input. And so the very top of this network, the goal of it is to get the input to a reasonable shape to start passing through these residual blocks. And now each of these with the, kind of see the residual going around, each of those is essentially another one of these residual blocks with a little bit of change of flavor here and there in various places. We'll get into that in a second. Here you have 3 residual blocks in a row where they're 3 by 3 by 64 because that was the input, the number of channels in the input. And you have 64 of yourself. So you basically, what you're doing here is you're taking the input and passing it straight to the output with no modification. So in some sense, these 3 layers are a no-op, right? Like if the weights in all of these incremental internal layers are low, these 3 layers do nothing. They just pass out the output as the input. And essentially then there's a little structure here we'll talk about in a second. But then it does it again. Then it does it again, then it does it again. So instead of having all 34 of these layers being relevant to getting signal back from the output to the input, you've created a chain where nothing's relevant getting from the output to the input. And so you can immediately start making reasonable updates to these parameters at the beginning of the network while you're simultaneously making updates to the parameters near the output of the network. And then hopefully these 2 processes will get your parameter values reasonable and you'll start to meet in the middle. But residual nets have one more insight than that. I mean, maybe even more than that, but one more that I'm going to talk about here. And that is this notion of a convolutional block that is a bottleneck. It's called a bottleneck layer, something along those lines, where there is no back channel. So that dotted line means that they're not passing the information. I don't know why they drew it in a dotted line instead of just not drawing it. Before I said like you're passing the information straight back. No, that's not quite what you're doing. But what you're doing is you're passing the information back and it goes through just a few layers, then you pass it back and it goes through just a few layers, then you pass it back and it goes through just a few layers, then it gets to the input. Now, this sized network is probably a simpler network than we just saw in the AlexNet, which had a lot of convolutional layers. And it could learn relatively quickly what are reasonable parameter values at these different points in the network and right at the end and then hopefully right at the beginning. And then from all of these spots, you can take these reasonable but not good enough yet and start to learn residuals around them. by starting to employ all of these other layers. So the residual network concept takes the signal that you have, propagates it to parts of the network, and then lets it slowly spread from those parts of the network to refine the concept that those parts of the network have learned and add just a little bit more value to it. So you're able to put many more parameters than you could learn at first, but learn them through this kind of like trick of skipping them and then allow them to contribute over time, etc., etc., etc. And at the end, it's fully connected Softmax, like everything. Here's the paper. I think I may have put that in the readings to just go take a look at it so you can kind of read through this and get a sense of what they're saying. But this was 2015, 60 million parameters, which I believe was the same actually as AlexNet. Maybe I was wrong on that. Ensemble of 152 layer networks. So they built multiple networks to 152 layers and then created an ensemble out of those and achieved human level performance on that same task that AlexNet was run on, where it got 17% error rate if you let it get a guess of 5. This system did as well as humans at predicting what was in those images. And of course they do data augmentation just like before and batch normalization, which we're not talking about in more detail. But you can just think of batch normalization as another layer that you can put between layers of the network using the tools, the PyTorch tools that we're going to talk about, that just regularize things a little bit, and that's all I'm going to say. Now, the final type of network I'm going to talk about, network structure I'm going to talk about, which is a little bit reminiscent of residual networks, is an autoencoder. The point of the autoencoder is, well, let's just go through this example to get the intuition of it. Imagine you have an input code. Let's say I input x1 equals to 0.1, and then I give it a particular image that I want the network to produce when I input x1 equals to 0.1. You can have a whole network here which is full of convolutional layers, whatever you want to do, all the fancy stuff that you want to set up, and all it needs to do is memorize that image goes with that code. Could probably do it, right? Doesn't seem crazy. You input a different code, 0.02, and you have a different image there. Okay, that's possible. Let's do it again. There's a closed eye image for a different code. What an autoencoder does is it takes that notion, but instead of you giving it the code, you say, go and learn that code. And in this network, that code is represented by that layer, and the code is a vector. Now, this should sound very familiar. When we talked about word to vec, we were able to transform a word into some sort of a representation of its meaning, and then go from that representation of the meaning possibly back to the word. It's precisely what an autoencoder does, or how you would train an autoencoder. You would take the input, you would set up a network structure that does all the tricks that we've been talking about, except that right in the middle of the network structure you have a really strong bottleneck layer, which contains far less representation capability than the image you're trying to represent. And you essentially tell the computer, learn a code that represents what's going on in my image with not nearly enough information to do it. That needs to be encoded in the rest of the network and with similarities between the code. And the code doesn't have to be a one-dimensional thing. In this example, it's a two-dimensional vector. Then you can do the entire network structure you did at the beginning in reverse, essentially, and have the output be the image you are trying to encode. If you run this across a whole bunch of images trying to predict the image from itself with this constraint that you're not able to, you have to somehow shove it through that bottleneck so that it can come out on the other side, you've created an autoencoder. And this representation can be a very useful feature to attach to other machine learning algorithms, or to attach in other situations. You could learn this from one neural network and then input these as inputs to another neural network later on for a different purpose, some like transfer learning, that kind of stuff. You call the first part the encoder, takes the image, converts it into the representation, and then the second part is the decoder and the bottleneck, right? So this is all the stuff I just talked about. Then, to just be extra clear, One way to use this is similar to what we did with Word2Vec, which is you train the network, you throw away the decoder, and you use the embeddings, which is this layer, as input features to go from a sparse representation like a two-dimensional image to a dense representation, which is a vector that represents kind of what is in that image. To illustrate this a little bit further, I'd like to talk about variational autoencoders and generative adversarial networks. I think that's what that means, but just at the highest level of concept of what they do. I'm not going to go through the techniques at all beyond what you saw on the previous slide, but this is another technique. You can train an autoencoder slightly differently, when you're right. Then you can find the embedding of any object. Then you can modify the embedding a little bit, and then you can decode the new embedding. From that sense, depending on how you've modified the embedding, you can potentially change an image in interesting ways that you can control. Let's go through a quick example. That's a picture of me without glasses, not the best picture I've ever took of myself. And if you were going to embed that into a two-dimensional space, you might find out that, hey, that's about where I am at. Now, if you have the right properties of how you built this so that things that are close to each other in this embedding space mean similar things, you can come up with another image of me. And the only difference here, I tried to have the same pose. Looks like the lighting's a little different. I didn't mean for it to be, but the only difference is that my glasses are on. You produce the embedding of, okay, well, that's where me with glasses and me without glasses is in this embedding space. And then you can calculate the vector. And that vector is the difference of putting glasses onto me. Now, right, that's the delta. Now let me take you and get an embedding of you. And that's where you are. Now, if I take that delta in embedding space that adds glasses to me, that delta in embedding space, assuming you've done a few little tricks there, will be pretty equivalent to adding glasses to you. So if I apply that, I get the new point, and then I decode from that spot, which is your embedding plus the delta of me with glasses and me without glasses. There's a chance that what I'm going to decode is going to look like you with glasses on. And here's an example of that from some of these papers. And if you hear things about like deep fakes, this is probably not exactly what's happening, but it gives you a sense of how you might go towards producing a deep fake. Right? And to just show this is a man with glasses, and you subtract out a man and you add a woman. So you're doing even more complicated algebra than what I did over here, where I'm just, glasses, but it's remove something and then add in something different, but leave the glasses the same. And here are pictures that they got from doing that added very similar glasses to all of these faces. Interesting stuff. That's a lot to cover, and we could easily spend another 10 lectures going back through these things in more detail and seeing all the math in a little more detail, and we could implement these. We could spend the next 5 years of our lives. But I think right now, hopefully you're armed with enough understanding of modern neural network architectures to get a sense of what it's going to take to use them, how important it is to leverage architectures of people that have come before you, and what type of trouble you're going to be getting into if you go into a completely different domain where you can't benefit from a pre-created architecture, or even more importantly, a pre-learned model that has weights sort of reasonable, that you can cut the network and snip your own kind of like concept there, benefiting from all the filters that the previous work has learned for you. We covered fully connected layers in the last thing, convolutional layers, max pooling to downsample, another form of activation which is easier to converge with and has nice properties for a large network, Softmax for turning uncalibrated outputs into something that sums up to 1, which is more like a probability, a whole bunch of stuff for other domains that we didn't even talk about at all, the notion of what an embedding is and how to do it with an autoencoder, residual networks, which is a way to spread information through a network to allow you to learn much more complicated structures much better, batch normalization, an important technique that I just decided to cut, dropout, which helps avoid overfitting, and patience I didn't get a chance to talk about, but it's the concept that as you're trying to converge a network on a holdout set, you continue running until loss stops going down. But because the parameter space of neural networks are so complicated, you may have the property that you're kind of like going like this and going kind of up and down and all around and whatever. And patience is just the simple concept that once the first time you think you should converge, don't. Give it a few more minutes. Try to run a few more iterations and see if you can get over a hump and continue converging even further. And that's an important technique when trying to get convergence in these really large deep neural networks. In summary, neural network architecture is the key. It's very hard to produce unless you have grad students to send out to descend on the problem. You're going to have a hard time coming up with major innovations in neural network structures. You're going to be better off leveraging something that exists, leveraging a pre-trained thing, and applying it to your domain. Architecture engineering takes the place of feature engineering, where you input a raw image without doing a whole bunch of normalization and stuff like that, but you've created an architecture that knows how to do the appropriate properties to help with the application you're working on. And it's not easy, and things are changing recently. And if you want to get good at this deep neural network stuff, go start reading papers. Probably going to have to read a lot of papers and learn a lot more math than we used in this course. Okay, but if you are in a domain with an existing architecture, if you have a lot of data, millions of data points, something in that ballpark, if you have a GPU or many GPUs or many GPUs for training, and you want to figure out how to move things between them, and you need the best possible accuracy, you have a domain where that extra like 98.4% to 98.8% really matters, like ad targeting, a small conversion rate change multiplied by all the ads that you have. It could be worth a lot of money, and there's plenty of domains that have that property. But if you really need to chase accuracy, try neural networks. Good luck to you. See you next time.